In section 13.5, I'll discuss power. In physics, power is defined as the rate at which energy is transferred between systems. Generally, we're talking about energy being transferred into our system, and that's what we refer to as work. Here's the basic definition for power and how to calculate it. It's energy per time, but this is what's going to give us the average power delivered to a system over some time interval t. And we measure power in standard units of energy and time, that's joules per second, and we have chosen to abbreviate that as watts. And a watt will break down into a joule per second. Remember that a joule can be expanded out into a Newton times meter, so a watt is also a Newton times meter per second. And remember that a Newton can be further expanded out into kilograms, meters, and seconds. So here are all the different breakdowns of a watt. Do you have to remember what a watt breaks down into? No, it could be useful, but you don't really have to remember it. What you do have to pay attention to is that if you want to get out standard units, you have to put in standard units. So if you want watts, you need joules, newtons, meters, seconds, kilograms. We have an alternate equation for power. If power is energy per time, and remember, energy is really the same thing as work, and work is force times distance, well, I could write that just a little bit different, and then you should notice that we end up with force times distance over time. Well, what was distance over time? This is velocity. So we can also calculate power as force times velocity. This is the equation for instantaneous power being delivered by a force. If the speed of an object is changing, and which is a common thing when energy is being added to a system, generally an object will change its speed, then we can't use this equation. This equation is generally only useful for situations where an object is moving with a constant velocity, or if we want to know the power being delivered at one given instant. And in that case, it depends on how fast it's moving at that instant. Just like work, only the component of force in the direction or opposite to the direction of velocity is going to deliver power. If a force is acting perpendicular to velocity, so for example, the normal force acting on a block sliding across a floor, in this case, the normal force acts perpendicular to velocity. This will deliver no power. It won't transfer any energy to the block because it's acting perpendicular to the motion. Okay. And if a force is acting in a direction opposite motion, it will deliver negative power, which means that it is removing energy from the system. And that's common for something like friction that may be acting opposite motion. Also, drag will tend to remove power or remove energy from a system and therefore deliver negative power. Okay, so I discussed two different equations to calculate the power delivered. And how are you going to decide which one to use? Well, generally, it's kind of obvious which one to use. Average power is energy per time. So if a time is mentioned in the problem, you're probably going to use this one. Instantaneous power is force times velocity. If a velocity is mentioned, especially if the velocity is constant, then usually we're looking at instantaneous power. So if the question asks about the overall motion and not just the motion of an object or a system at a specific time, usually we're going to be looking at the average power. And in these situations, it's very common for the speed to change. So if the speed is changing, usually force times velocity isn't going to be useful because what value would you use for velocity? If we're asked about the power delivered at a certain time, or if the velocity is constant, generally we're going to be looking at the instantaneous power form of the equation, the force times velocity form of the equation. Now, in the special case for a constant speed, well, then average power and instantaneous power are the same value. The power being delivered is constant for a constant speed. Basically, in that case, the energy in is the same as the energy out. So in the case where the speed is constant, you could really use either form because they are equivalent. Okay. In this example, we have a loaded freight elevator with a total mass of 1,200 kilograms, and it's going to rise to a height of 60 meters over the course of 3 minutes, and it starts and it ends at rest. If we assume there is no loss of energy due to drag or friction, part A wants us to find the average power delivered to the elevator. So if we think about the forces acting on the elevator, there's going to be the elevator's weight that acts down, and we can calculate that weight. That weight is m times g. And we can calculate that by multiplying the mass given as 1,200 times the value of g, 10. So the value of the weight will be 12,000 newtons. In order to lift the elevator up, there's going to have to be a force up. In this case, that is the tension force, the tension in the cable. And the has to provide that tension force, the motor that provides that tension that pulls the rope to lift the elevator up is going to provide that tension force. And the elevator is going to move through a displacement that is up. Now, if we want to find the average power delivered to the elevator, well, in this case, we're going to use the power is energy per time. And in this case, the energy that we're talking about is the gravitational potential energy that the elevator gains. And in order for that to happen, the tension force is going to have to do some work, right? And so the gravitational potential energy that we're going to gain is going to be m times g times h. I found the value of m times g. That was the 12,000 newtons times the height that the elevator is lifted, and in this case, that's 60 meters, divided by the time that this happens. Well, that's 3 minutes, but we don't want to be in minutes because we want to get out watts. If we want standard units, we want to put in standard units. And 3 minutes times 60 seconds per minute is 180 seconds. And so our average power to lift this is 4,000 watts. And when we're in the 1,000-watt range, it is very common to see that expressed in kilowatts. So there are 1,000 watts in a kilowatt. Okay, at some time in the middle of the motion, the elevator was moving at some constant speed, 0.5 meters per second. And it should be noted that that is less than the average speed because the elevator had to spend some time slowing down. What was the power being delivered to the elevator at this time? We should expect the power being delivered to be higher than the average at this time. And since we're looking at power at a specific time, we're looking for instantaneous power delivered. So we want to use the force times velocity equation. The force that we're talking about here is the tension force. And here it said that it was moving with a constant speed. Well, constant speed implies the force up has to equal the force down, right? The forces have to be balanced for the elevator to move at a constant speed. And so the force pulling the elevator up has to be the same as the elevator's weight, that 12,000 newtons. We're going to multiply that by the 0.5 meters per second. And so the instantaneous power being delivered to the elevator at this time is going to be 6,000 watts or 6 kilowatts. In this example, we have a drag car with a mass of 3,000 kilograms, accelerated from rest to 50 meters per second. 50 meters per second is about 112 miles per hour, and this is done in 15 seconds. If we assume no loss of energy due to drag and friction, we are to calculate the power output of the car's engine. And so in this case, notice that we are given a time. And so the version of the power equation that we should use here is energy per time. So we should note that the drag car starts from rest. So the drag car is really starting with no energy. And we can calculate that energy. That energy is going to end up, the increase in energy is going to be work performed. Well, remember that work is just the change in energy. We started with zero energy, and we're going to end up with some kinetic energy at the end. Well, how much kinetic energy did we end up with? Well, we can calculate that with the mass and the speed. Inserting the values for the mass and for the speed. Don't forget to square that speed. We end up having 3.75 million joules. 10 to the 6th is a million. And so we can put that into the equation here. 3.75 million joules. And we're going to divide that by 15 seconds. That will give us our power as 250,000 watts, which is also equivalent to 250 kilowatts. Now, since we live in America and we don't like the metric system, we are still stuck measuring the power output of vehicles with horsepower. Horsepower is an alternative unit for power that we still use here. And the conversion from kilowatts to horsepower, for every 1 horsepower, there are 0.746 kilowatts. So horsepower is a little bit larger than a kilowatt, and this is 335 horsepower. Interesting little tidbit, the horsepower was actually introduced by James Watt. Remember, James Watt had improved the design of the steam engine, and this was done when society was mostly agrarian. Most people had a farm, and so this was a really useful unit for the society at the time, because if a farmer was going to invest in a real new technology, he needed to know how many horses it was going to replace. Horses were expensive, and if you're going to invest in something even more expensive than a horse, like the steam engine, you need to know how many horses it's going to replace. So that's the origin of the unit horsepower that we still use in America. So in part B, it says, imagine that the car had a power output of 750 kilowatts. How long would that take to accelerate from rest to that same speed of 50 meters per second? Well, notice that the power output was 250 kilowatts in part A. 750 kilowatts is 3 times the power. Right? If we have 3 times the power, how much time do we need? Well, power is energy per time. Well, what's the relationship between power and time? Well, power is inversely proportional to time. So if we increase the power, we will decrease the time. We will decrease the time by a factor equal to the inverse of this increase. If we increase by 3, we will multiply the time by 1/3. We'll decrease the time by 1/3. And it took 15 seconds to go from rest to 50 meters per second with the original engine. So 1/3 of 15 seconds is 5 seconds. So increasing the power decreases the time for the same task. On the last slide, I talked about an alternative unit for power, the horsepower, which is equivalent to just a little bit less than 3/4 of a kilowatt. On this slide, I'm going to talk about some of the alternative units of energy that you may find in your everyday life. So power is defined as energy per time. So if we rearrange this for energy, we get power times time. So if we take a unit of power and multiply it by a unit of time, then we get a unit of energy. So we could take a watt times a second and we get the joule. Well, we have this very common energy unit called the kilowatt hour that is very common for measuring electricity, because the power delivered by the energy company is usually measured in watts or in kilowatts, and if you multiply that by the time that energy is being consumed for, then we can get how much energy usage we have. So to convert the units of kilowatt hours into joules, here's how we do it. 1 kilowatt times hours. We can get rid of kilowatts and go to watts, and there's 1,000 watts in 1 kilowatt. Kilowatts will leave, and now we're in watt hours. A watt is a joule per second. That's the definition of a watt. Watts go away. And now I want to get rid of these units of time. I just want to be left with joules. So to get rid of hours, I put it on the bottom, and I am dividing by seconds up here. So if I multiply by seconds, that will get rid of divided by seconds. And there are 60 times 60, or 3,600 seconds in an hour. I can lose my units of hours, lose seconds. And now we see that 1 kilowatt hour is equal to 3.6 million joules. So a kilowatt hour is a useful unit for a large consumption of energy, which is why the energy company will usually send you a bill billing you for X amount of dollars for each kilowatt hour of energy that your house consumes. Heat and thermal energy can also be measured in some alternative units that you may have seen before. First is the calorie. A calorie is the amount of heat energy that it takes to heat 1 kilogram of water by 1 degree Celsius, which is 4,186 joules. So a calorie is a rather large unit for energy. You may have also seen this. This again is left over from previous systems of measurement, and we still will use this here in America because we are hesitant to change. BTU stands for British Thermal Unit, and this is the energy to heat a pound of water by 1 degree Fahrenheit. So notice these are English imperial units. You will sometimes see these on appliances. Here's an interesting one. This comes up if we are talking about the energy output of explosions. We can measure that in tons of TNT. So a ton of TNT is the energy, the thermal energy that is output by exploding or combusting a ton, that's 2,000 pounds of TNT. And of course, that's going to be a extremely large energy output, 4.184 billion joules of energy per ton of TNT.